One thing we can use implicit differentiation for is to derive the formulas for the derivatives of inverse trig functions. In this video, we'll derive the formula for the derivative of inverse cosine. Let's start from a graphical perspective, and let's think first, instead of inverse cosine, about the graph of cosine. So if theta is the inverse cosine of p, that means p must be equal to the cosine of theta. On the horizontal axis, we have theta, and on the vertical axis, we have p. The problem when we go to do the inverse is that this graph of cosine does not pass the horizontal line test, which means its inverse will not pass the vertical line test. So you may recall from pre-calculus, we get around that by restricting the domain of cosine, so that we just look at the part of the graph that includes every value that cosine ever takes on exactly once. And by convention, we choose that portion from 0 to pi. See what the graph of inverse cosine looks like. We simply flip the x and y values of this yellow shaded part of the graph of cosine. So now, instead of p being on the vertical axis, it's on the horizontal axis, and theta is now on the vertical axis. So now we've got theta equals the inverse cosine of p. So pause the video now and try to sketch what you think the graph of the derivative of inverse cosine will look like. Okay, so one thing you probably notice is that the slopes of all the tangent lines here are negative. So we're never going to need any positive values for the graph of the derivative of inverse cosine. So let's make the axis look like this. This is going to be theta prime. Here's -1, here's 1. And at the endpoints here, those points on the graph of inverse cosine came from these points with horizontal tangents on the graph of cosine. So we're going to have infinite slope, infinitely negative slope there, undefined slope. Those are going to be asymptotes. We have our smallest negative slope, or our closest to 0 negative slope, when x equals 0. We have very high negative slope out here, and then very high negative slope out there. So the graph looks something like that, the graph of the derivative of inverse cosine. Now that we have an idea of what the graph of the derivative of inverse cosine looks like, let's use implicit differentiation to actually figure out what is the equation for the derivative of theta prime. Now remember, if theta is equal to the inverse cosine of p, then p is equal to the cosine of theta. So these two equations, this one and this one, are saying the same thing in different ways. Let us then take the derivative of this one, where we know the derivative of everything. We want d theta dp, so let's take the derivative with respect to p of both sides of this equation. Pause the video and see what you get if you try to implicitly differentiate that equation. What I get is this. ddp of p is 1, and ddp of cosine of theta is minus sine of theta, times, because I'm differentiating with respect to p and theta is a function of p, times d theta dp. Now this d theta dp is exactly what I want to know. So let's just solve for that by dividing both sides by minus sine of theta. So I have d theta dp equals -1 over the sine of theta. So now we have the derivative of the inverse cosine of p. However, it's in terms of theta, and normally when we have a derivative formula for a function, we want it in terms of the variable that the function's in terms of. So we would like that to be in terms of p instead of theta. All right, let's give ourselves a little more room here. d theta dp we know is -1 over the sine of theta, but we want to write the sine of theta in terms of p. And Just a little bit of right triangle trigonometry can help us out. Let's work on a unit circle here. So I'll draw a circle with a radius of 1 and an angle theta. And remember, the coordinates of any point on a unit circle are cosine of theta, sine of theta. So that means the height here is sine of theta, and this side is cosine of theta. And we know that sine squared of theta plus cosine squared of theta equals 1. Cosine of theta, remember, from up here is just p. So we can write sine squared of theta plus p squared equals 1. And that tells us that sine of theta is plus or minus the square root of 1 minus p squared. We can do even a little bit better here if we remember that we've restricted theta to having to be between 0 and pi. And if an angle is between 0 and pi, its sine, the y-coordinate, is positive. So in fact, we know that the sine of theta has to be the positive square root of 1 minus p squared. So we can replace 1 minus p squared for sine of theta. So we have what we were looking for here. D theta dp is negative 1 over the square root of 1 minus p squared. And remember that theta was the inverse cosine of p. So we now have a formula for the derivative of the inverse cosine of p, and it is just negative 1 over the square root of 1 minus p squared. And we don't want to have to do that again, so we're going to remember that. Before we leave this entirely, let's go back and look at the graph that we made at the beginning of all of this. So we have that the derivative of the inverse cosine equals negative 1 over the square root of 1 minus p squared. Does that make sense with the graph? Well, we can't have p squared equal to negative 1 or 1 because that would make the denominator 0, and p squared is going to have to be less than 1 because we don't want a negative inside the square root. So we've got that p has to be between negative 1 and 1, which is what our graph shows. And we also have that if p is 0, this would have its highest value, which will turn out to be negative 1. So we can even put that point in on the graph. And as p gets closer and closer to 1 or negative 1, the denominator of this expression will get closer and closer to 0, which means that the whole expression will get closer and closer to either plus or minus infinity. And the negative on top assures that this expression is always negative. So the graph makes sense. Excellent. And for the very last thing, let's see how we'd actually use that formula. So I might use that if I'm asked to find the derivative of a function like the arc cosine. Remember, arc cosine is just another way of writing inverse cosine. Arc cosine of x cubed. So pause for a minute and see if you might come up with what the derivative of that function might be. Okay, I see a composition here. So my baby is x cubed. My mom is arc cosine. So for f prime, I'm going to take the derivative of the mom, which is arc cosine. So that's negative 1 over square root of 1 minus, now instead of p squared, I have to put the baby in there, so that's x cubed. There's the derivative of the mom, keep the baby inside, times the derivative of the baby, 3x squared. So I have f prime of x equals negative 3x squared over the square root of 1 minus x to the 6th. So you never have to do again all that stuff we did above to derive this formula, but we're going to need to use that formula when inverse cosine shows up in something we're asked to take the derivative of.